problem, so I want to repeat it slower with more details, because this problem is absolutely identical to all other similar problems. And there's a question which I want to ask officially now. If you came here earlier, you had more time to think about this question. Now it's for everybody. And well, if you just came, you can say, well, it's not fair. Those people had more time. And I would say, yes. Life is generally unfair. Today is everything working. Yesterday it didn't. Yeah, imagine staring for 30 minutes at the same question. Boring. So, every time, from the day one, when we needed to solve a problem, what did we always do? A picture. Even if it's given to us, we still draw it. And when we draw it, even if we're absolutely alone, we have to say out loud everything we do. We have to. Why? Because that's how we help ourselves to think it through. Pre-med students probably know that every action, verbal, kinetic, excites an additional number of neurons, brain cells. So every single action helps, and if you don't want to help yourself, you're punishing yourself for something. Don't do that. So I'm drawing a board. Why? Out of all the objects, this one is the most interesting. It's experiencing forces, but despite that fact, it's in equilibrium. What forces does it experience? Well, clearly, since it's not massless, there is a force of gravity applied to the board. And since the board has a uniformly distributed density, the force of gravity acting on the board applied to the middle point of the board equals mg, or 12 times about 10, 120 newtons. And as we know, an additional force of gravity acting on the lady, but she pushes on the board. It's kind of interesting question. The force acting on her is 530 newtons. So why do we say that the force acting from her on the board is also 530 newtons? What do you think?
I'm not sure what you're asking.
The force acting on the lady is 530 newtons. The force I'm drawing right here is not acting on the lady. That force is acting on the board. Why do I say it is equal to 530 newtons? What's the reason? Yes? I guess that's thinking in the right direction. However, if we want to prove something in physics, we have to stick to definitions or laws. So what law did you use? And I'm just giving time everybody to answer this question. What law of physics did we use to make it transition from the given number acting on her to this number acting on another object on the board? Well, so far here we have no mentioning of energy at all, right? No energy, no momentum. We talk about forces, and when we talk about forces, what laws do we usually use? Yes? Newton's third law, because here we have interaction between two objects. There is a force acting from her on board, and there is a force acting from board on her, and these two forces must be equal to each other in magnitude. So F1, F2, and that is the Newton's third law. But still, it doesn't say that these forces must be equal to 530 newtons. So we got to use at least additional law. Newton's second law, absolutely. So you see, it looks like a very obvious situation, but we actually had to use officially two laws. We also should say that since she, the lady, is in equilibrium, that means forces acting on her should cancel each other out, which means this. And this is due to, so this is Newton's second law for the lady. This is Newton's third law for the interaction between the lady and the board. And now we got 530. So it's, actually requires some proving. It's like a theorem in geometry, which people usually hate. But now we know, or else we should add, well, from the fulcrum pivot, normal force, and here, as we said, the force which holds it. And here I have, again, same situation, modeled. Well, if you look at the numbers, they're different because, of course, we have more of the board here, so more gravity. If we add some weight, it changes. But if we put it at the end, you can see now it goes in opposite direction. Yep. This is when I push. And this means that actually the board acting on the scale exerts the force upward, which means the scale, which this is kind of bolt, holds it. If I release it, what's going to happen? I knew that would happen, and I did it anyway. So clearly, again, there is that critical location between a stable situation and unstable situation, somewhere here, when this force starts to be equal to 0. Oops, somewhere here. And we can calculate this location, we can calculate those readings if we need to. In this problem, we actually need to calculate kind of these readings, these two forces. That's what we need to do. So, the torque of the force acting on the board from the bolt is, and people said everything. The answer number 3, oh, sorry, wrong. The answer number 1 is the most popular answer. Well, let's see. This is my axis. Does it change your answer? Here. So what did you choose? You are correct. everybody else is wrong. Because that's exactly the question everybody should have asked. Where is the axis? Without giving the specific axis, we cannot answer the question, because relative to this axis, it's 0. Relative to this axis, it will be counterclockwise, which is positive. But again, no one tells me what to do when I choose the axis. I can choose it here. Why would I do that? Just for fun. But that would make the same torque negative. So you should have asked, and if you didn't, write down a note. Check the axis. If there is no information about the axis, we can't answer this question. So the right answer in this particular situation is no way to say. And now, this is where I want to select my axis. I'm going left, right. That's so relative to this axis, we have 1, 2, 3 lever arms. And relative to this axis, it actually helps just to draw we have 1 counterclockwise torque, and we have 2 clockwise torques. And now we can balance them out. And the equation for each individual torque is this. The magnitude of a torque is equal to the magnitude of the force times the lever arm of the force. And the equation, which we call torque balance equation, says one of the version. We have 3 versions. We have 3 versions for the magnitude of the torque. We have 3 versions for the torque balance equation. So, since you look at me, which version do you suggest should we use? First, second, or third? Say third. Okay. So what does it say? It says that if we add all counterclockwise magnitudes, this is kind of slang, we should say all magnitudes of torques which directed counterclockwise. Yeah, but if we add all counterclockwise magnitudes and we add all clockwise magnitudes, again, a slang, we should say magnitudes of torques directed clockwise, the result must be the same. The sum on the left should be equal to the sum on the right. So how many counterclockwise magnitudes do we have? How many torques which point counterclockwise? 1. So we have only 1 term on the left and 2 terms on the right. And now for each we have to apply the same equation. So normal force do we know it? No. So we write a number. We don't write a number, we write a variable. The lever arm for the normal force in this situation, this distance, R1, and that's going to be equal to 1.4. Done. Now, on another side, we have 2 terms. One is from the force of gravity acting on the board, and we need to use distance R2. And we know that it has to be equal to a half of the total length. And this is total length. And a half of the total length will be literally a half of 3.9 plus. And the last term, so the force is 530. And the lever arm, again, we all lever arms measured from the same axis. That's why rushing is bad. And that's going to be equal to the whole length. Now this equation has only one unknown, so we can immediately solve this equation for the force. What do we do next? Next we shift the axis at a different location. And well, that requires slightly different diagram relative to this axis. The equation looks slightly differently. We still have one counterclockwise torque and two clockwise, but all lever arms are different now. So with a counterclockwise torque, we should write force times the lever arm. The lever arm is this distance from the fulcrum to the bolt, 1.4. Should be compensated or balanced out by two others. So the forces are the same. 120 is the force of gravity acting on the board. But now we have to use a different distance. It's shorter one, this one. So to get this distance, we need to use geometry. That's supposed to be equal to a half of a board minus 1.4. 1/2 of the length of the board minus 1.4. And now we need to add same force, 530 times. Now it's got to be this distance. And that's total length minus 1.4. And in this equation, we only have one unknown again. And we solve it, and we're done. So that's the strategy. So we've done it again, and a couple of more times coming up. So here, something you can actually read. And any questions on this strategy? Yes? Yes, the question was calculate force acting from the bolt, calculate force acting from the fulcrum. Now, we could have used torque balance equation and then force balance equation. Because if we draw a free body diagram, bolt, normal, 120, 530, force balance equation, which is very old-fashioned, well-known equation, net force equals 0 relative to y-axis. We should write normal will be equal to this plus this plus this. This is an additional equation, and if we use this equation to solve for the normal force or to solve it for the force from the bolt, we should get the same numbers. So you can use this to check if your mathematics and equations were correct. If you calculate normal force from here, from first equation, and from second equation, and then, for example, you just plug numbers in here, you should get an identity. Just to check. Okay, so again, the same situation, and let's just so what do we have? A board is not massless here. The total length of the board is 20 plus 60 plus 20, 100 centimeters. So the total length of the board is 1 meter. And you place a weight right at the top of a second scale, and your task, your goal is calculate the readings. So please draw a diagram. Draw a diagram. Choose a location for, well, one axis of rotation. And write the torque balance equation relative to that choice of yours. And strategically, this problem is now different at all from the problem we just have solved. So please, again, copy picture, draw diagram, we'll show all the forces, pick one axis of rotation, and write torque balance equation relative to that axis. Then, write the time when you finish doing that, then take your very, very smart phone, take a picture using that phone, and email it to me. This is why having a smartphone is important. Yes? Yep. No, it's 1,000.
The other one shows 500.
I have enemies. Everybody does. You better know yours. Thank you for catching it up. So again, please draw a diagram, choose axis of rotation, or write torque balance equation, take a snapshot and email to me, please. I'm gonna wait. This is the hardest part of my job, doing nothing. So please draw a diagram, choose axis of rotation, write torque balance equation, take a picture, email to me. Okay, thank you. I see the diagram, but I don't see the equation. Your picture should include the equation, TBE, written relative to that axis you chose. So please resend the picture with an equation. Now, the equation which I'm asking for is not the force balance equation because it's too easy. The equation I'm asking for is for torque balance equation. So please resend the picture. Don't be afraid to make a mistake. I made a mistake yesterday. It's not about not making mistakes. It's about fixing them. Everybody makes mistakes. Mistakes are inevitable and unavoidable. The easier we feel about it, the better. What really surprises me is the silence in the room. You know, you can talk to each other, to yourself, to higher power if you believe in it. I mean, the chair of physics department, he's on the second floor. Higher power. Okay, now we're getting there. Yeah. So it also takes some time to process the emails. But now I see many of them. Well, the object of the interest is the board. We know it is 1 meter long or 100 centimeters long. And actually we can use grams, centimeters. And so we have one force acting here, 20 centimeters away from the left end of the board, and we have another force acting here. Those are normal forces. They point up. Different? Well, we don't know, but our expectation is because there's additional weight. And so this is also 20 centimeters away, but from another end. And we also have force of gravity acting on the board. And because of an additional weight placed right here, we also have a force acting from a weight on the board, and that force has magnitude equal to mg. Big M here is the mass of the weight. So little m is 100 grams or 0.1 of a kilogram. A big M is, bless you, 1,000 grams or 1 kilogram. That's the diagram. That's a free body diagram. That's not torque diagram. There's one little thing, one simple element and action which should be done to convert this free body diagram into the torque diagram. What should we do? Yes? And where did you choose your axis? On the right to what? The right is a very wide region. So can you be more specific? Where did you choose the axis?
Yeah, where above the scale.
Here.
Yep.
At the location of the right scale. So let's choose it here. This is the most convenient choice at this point because it eliminates two torques. Two birds with one stone. Now, relative to this axis, let's call it, we can write the equation. And now what we have is torque due to gravity, positive or negative? Counterclockwise positive, and this automatically clockwise is negative. And these two forces are not equal, but they have no torque. So our torque balance equation here is very simple relative to this axis. F normal 1 times, well, 60. That's this distance between the scales. 60 or 0.6 meters were, okay. And that should be equal to the magnitude of 0.1 times 10 times, that's supposed to be this distance. Now, please tell me what number should I write? Yes? Why?
Gravity is always at the center.
So we use this fact that this has to be equal to a half of the board. So this is 1/2 of 1. And this is 20. So we got to do a little geometry here. 50 minus 20, 30 centimeters, or 0.3 if I use meters. So 0.1 times 10 times 0.3 over 0.6. A half. Yeah, 0.5. Whatever. And now, actually, we are ready to use, well, we can, again, choose between what do we want to do. We can shift the axis of rotation, or we can use force balance equation. Let's do it now. We haven't done it before. So relative to this axis, what should we write? We should write that normal up plus normal second up should be equal to mg plus mg. So we can use it to calculate second normal. It should be equal to 0.1 times 10 plus 1 times 10 minus 0.5. 10.5. Any questions? All right, in general, actually, you can solve this problem algebraically for any possible location. It's kind of like here, and you can see what's going to happen to forces if you move the weight along the board, left or right. Now, you know the rule of thumb. Oops, where is it? Here. Use your legs, don't use your back. That's actually based on physics. This is just a rough estimation for average person. How much stress would you pull on your spine if you would be lifting an object like this? Same kind of reasoning. You choose the axis and you calculate the force using torque balance equation. And it turns out that if you try using your back muscles, the force acting on the spine, on the compressing vertebra, is almost 2,000 newtons. It's like 20 kilograms. So that's why people say, use your legs, not your back. Now, we say it again and again and again and again that force of gravity is applied to a single point. We call it center of gravity. In general, it's one of the versions of the center of mass. But why? Well, how would we actually find that point, the center of gravity? Well, we use a scientific method which is called guess and try. We can guess. Let's say this is my center of gravity. According to a definition, I can replace all forces of gravity acting on small parts with one large force acting here. How can I check if I'm correct? If that is the center of gravity, and if I suspend this object at the center of gravity, it must be in equilibrium. If it's not in equilibrium, that point of suspension is not center of gravity. That's it. Why is it supposed to be in equilibrium? Well, because here we have only two forces, tension and that gravity. And if this is a center of gravity, first of all, these forces cancel each other out. Secondly, net torque is zero. If it's not a center of gravity, it's not going to be in equilibrium. So let's say I have a bat. Is this a center of gravity? No. Where is it? No. This is how I find it. When I find the point where it's in equilibrium, the center of gravity is here. You can do it with anything. More importantly, this idea is very useful if you need to calculate center of gravity or find center of gravity of complicated objects. Like here, it's in equilibrium. What does it mean? It means the center of gravity is supposed to be somewhere on this line. So, do you know what that is? A plumb bob. Somewhere here on this line, we should have the center of gravity. We cannot have it there or there, because that would make it swing. So what do? We take chalk, draw a line. All we need to do is another line. So we just suspend it to a different point, draw another. That's the center of gravity. So technically, that should be in equilibrium. Close enough. But we need to remember that the center of gravity is a point, a fictional point. It doesn't have to be inside of an object. Here, one line. Second line, the center of gravity will be here. How can I check it? Well, we have two options. We can throw it, and I'm not going to do that. And watch how this point moves, and that's supposed to move like a standard projectile motion object. Or we can attach something very, very light but steady and try to do the same thing with a finger. And of course, again, for a regular object which has uniform density, center of gravity will be in the middle. Otherwise, if we try to suspend it here or somewhere else, it would be moving. It wouldn't be in equilibrium. Here, this is a situation when we can use the same theory to actually calculate the location of the center of gravity. Well, how do we do that? Well, according to a definition, if we suspend or keep this system at the center of gravity, it should be in equilibrium. What does it mean? It means that one force, which generates clockwise torque, and another force which generates counterclockwise torque. These forces and torques that should be canceling each other. So in this problem, this is what we're looking for, distance. What can we do? Well, we have to write torque balanced equation, and on one hand it should be mg times, well, we already have all distances, a half of a meter minus distance we are looking for. On another hand, it should be equal to the mass of the ball times distance we are looking for. What do we have? We have 100 grams, 10, 1/2 minus 6, 210 x, 1/2 minus 6 equals x, 2x. 1,000, 2x. So 1/2 equals 3x, x equals 1/6 of a meter. So clearly, when we change the density distribution, if it's not uniform anymore, center of mass shifts, but it shifts toward the heavier parts of the system, like here, yeah. Any questions? So I did that. This is a picture from Wikipedia, Leaning Tower of Pisa. What's the difference? Want to see one more time? What's the difference? It's all about torque. So this was the first situation, yeah? Something like this. So where is center of mass? Somewhere in the middle. So we have force of gravity, and we have normal force. Well, forces cancel each other out, but it's all about torque. And let's say this is the axis, counterclockwise, clockwise. They do cancel each other. What's going to happen if we make it taller? Center of mass shifts. So now gravity, normal. But relative to this axis, clockwise, clockwise. also clockwise. So net torque is not zero anymore. We gotta, if we want to prevent it from falling, like here, we have to do something else. We have to maybe add some extra mass or hold on it, put some extra structures, but without anything else. Maybe glue it up. Yeah. But if nothing helps, that's it. Only two forces is going to fall. All right, don't really pay attention to this slide. It's mostly to make a transition from what we've talked about to what we want to talk about soon. We have done this experiment with a simple object on a string. We give it a push, and it stops. That's what it is. Why does it stop? Friction. What's good about this situation, we can solve for anything we want to. There is tension, there is friction, it's very small, it's not a rotational motion, it's a circular motion. And we know everything about it. And this situation tells us that when the circular motion is not uniform, it slows down, speed changes. If it's not uniform, the acceleration actually should have two components. So how does net force point? Friction, tension, net force should point like this, which means actual acceleration, net force divided by mass, should point like this. So actual acceleration should have two components, one toward the center, still same centripetal acceleration, still v squared over r. However, because it slows down, or could have been speeding up, there is another component which is tangent to trajectory, which changes speed. That component we used to call linear. Now we can call it tangential, because everybody calls this tangential. The actual acceleration, of course, is just Pythagorean theorem of two components. We don't need that. What we need is, we want to use this experiment to make a transition from linear variables to rotational angular variables. Instead of force, we want torque. Instead of linear acceleration, we want angular. And what do? Algebra, multiplying by radius, force times radius, torque. This is the equation which we use for a single point making circular motion. What is a rotation? Oops. That used to be here. A rotation is a combination of many individual circular motions. That's it. So what do? Since we know that when a solid object rotates, all individual parts have exactly the same angular velocity, angular acceleration. So we can write the same equation for each individual point and just add them up algebraically. And when we add them up, instead of all individual torques acting on all individual parts, we get the net torque acting on the whole object. And since they all have the same angular acceleration, it's still going to be exactly the same angular acceleration. But now, you see this combination, a mass of a single point times the radius for that single point. When we add all things up together, the result depends on the shape. Mass distribution depends on the shape. So that's why we have to use this equation to relate net torque and angular acceleration. And this, well, this has been calculated for us. You can Google or find in the textbook. Depending on the shape, this variable has a different coefficient. This coefficient, capital C, has a name of form factor because it depends on the form, on a shape. Form factor, ring, cylinder or disc, sphere, that's it. That's why we need to know the name of that object, because the name tells us what coefficient should we use? What form factor should we use? That's it. That's all I want to say about it. Just fun fact, nothing else. Interchangeable. Right? Okay. An example. What do we do if we have a combination of different shapes together? What we have here is a disk and a small ball attached to it. And what is wrong to do? Because I've seen it before. Don't add masses. So wrong. 50 grams plus 200 grams. I'll convert into kilograms times radius squared. That is wrong. What we need to do, if we need to calculate this variable for the whole system, we need to add these variables, i's, moments of inertia, for each part of the system. That is correct. Correct. Just remember that, and you will be all set. In this particular example, what does it mean? For the ball, do you see here anything which says a ball, B-A-L-L? So what do you do? What equation do you use? No. In natural intention, I agree, but not. What equation do we use? Small mass, exactly. That's the difference between a sphere and a ball. When we say ball, we think something very small, has no size. When we say a sphere, it has a size. So here, we should use small mass, that's it. Bless you. So, m r squared. Now, this is what? Oh, wrong. That should be k. What does it say? It means we have to use 1/2 m r squared. That's it. The rest is just using International System of Units correctly. .2 squared plus 1/2 times 0.2 squared. What is a unit? It has no special unit. It's just a kilogram times a meter squared. What might be confusing about it? Well, for example, this m means meters. This m means mass. A very common situation in physics. Same letter, completely different meaning. Any questions? Yes?
How do we determine the R for the ball? Is it just the same?
Because it has no size. Because it's a small mass. This is, oops, blue and blue, we cannot see. Green and blue, we cannot see. Okay. This is the distance from the center of a circle the small mass makes, but the picture says it's exactly equal to the radius of this disk. So we got to use the picture. Question. How do we move it? In order to increase the moment of inertia of the system, we need to move the weights. Okay. So there are two situations. Close to the middle point. So that's one situation. Second situation, when we move these masses away from the center, do I change the mass of this system? Now, what do I change? The mass distribution. That's what I change. I distribute the mass differently. Should that affect the moment of inertia? Yes, it should. So the question is how. And here, I got some toys for you, sir. Well, you got to stand up. And for you, because you're here, just try to do this. Do you feel any difference?
Between these two?
Yeah.
Yeah, this one's a little bit heavy.
You mean heavier?
I mean, maybe its center of mass is farther out.
Yeah, just try to move them the same way and see. This is, again, a very rare situation when you can trust your feelings. Do you feel any difference?
Yeah.
Can you describe it in words?
This one harder, the blue one.
Harder to do what? Just harder on the touch?
To like turn.
Harder to turn.
It's harder to change direction on this one.
Yeah.
As opposed to this one.
But if you feel the masses, they practically the same. They do the same, 500 grams each. So what do you think makes them feel different?
The mass is distributed towards the end.
Yeah.
So did you answer this question? How did you answer this question?
Away from that.
Away. This is what is hidden inside. The same situation. This is kind of difficult to rotate, and this will be much easier. So here we have the same masses, but which is heavier. Okay, here the masses are very close to the middle, and here the masses are very close to the edge. And here, which is which?
This one's on the end.
Okay, so here your masses are here, and this one, very easy. So I suggest, before you move, just play with this. Get that feeling. Thank you very much. So, of course, the answer also can be proved mathematically very easily. When we shift the masses away, we do not change this part. We change this part. And we don't change masses. We increase this distance. And of course, if we increase this twice, this actually quadrupled because r squared. So when we concentrate the masses further away from the center, that increases the moment of inertia. And that explains the difference between the moment of inertia for this thing, which is mr squared, and this. Because these both have the same mass, same distance, same radius. But how do we make this from this? We have to take all this mass and squeeze it. We don't take it out. We shift it farther and farther away. So that's why this guy has more inertia than this guy. Don't answer this question. I want to skip this. So what do we have here? A sphere and a disk. Same mass. This is this situation. Same mass, same size. The only difference is the shape. But now we know the shape affects mass distribution. Mass distribution affects rotational properties, moment of inertia. That's why I bought it, using as a stand. So, the easiest way when we need to compare what might happen is to solve it once in general. So, in general, for any object, this variable is equal to some coefficient, which we call a form factor times mass times some distance squared. For round objects, that's a radius squared. And what do we have? Here is net torque should be equal to moment of inertia times angular acceleration. And we need to figure out which we're going to spin faster in a second or in a minute. So they start from rest. Angular velocity is 0. And technically what we're looking for is for angular velocity later. Angular velocity, initial, final, time, and the angular acceleration are related. We use those equations. Angular acceleration equals delta omega over delta t, or final minus initial over time, or in this situation just final over time. Hence, this should be equal to this times this, or now if we use the Newton's second law for rotational motion, that's going to give us torque, form factor, m, r squared, time. The only difference in this problem between two objects is the form factor. When form factor goes up, how does it affect final angular velocity? Down. It's inversely proportional. It's in the denominator. So, you know what? Answer this question. I expect 100% correct answers now. This is question 4. Please tell me what you think. When form factor goes up, that slows down. Of course, when form factor, that number c, goes up, that means the system has more and more inertia, so it's harder and harder to change its velocity. So all we need to do now is to compare two numbers. The question is, which will spin faster? For the faster spinning object, the form factor should be... How would you finish this sentence? Smaller or lower? Yep. So now we need to compare two numbers, 1/2 and 2/5. Choose the number which is the smallest. Pick the name of a shape related to that number. Enter question 4. And you're going to be done. And what did you say? Sphere. The easiest way to compare two fractions would be what? Just to review, refresh. How do we compare two fractions? 1/2, 2/5. One way, common denominator. 1/2 is 5/10, 2/5 is 4/10. Or there is another way. 1 divided by 2, 0.5. 2 divided by 5, 0.4. You're right. All right. Yeah, I brought too much stuff. This is something like this. It could be a spool, a wheel, a string, and in this situation we just pull on it. We apply force by our own hand, and all we need to do is just calculate what force should we apply to have acceleration to be equal to 20. Well, question. Just please tell me, in this particular experiment, right here, right now, when I pull on the string, how many forces are acting on this wheel? Watch again. How many forces? How many forces? Zero?
Three.
Three. Okay. Which are tension,
Gravity and normal.
gravity, and normal. Does my hand touch it? No. My hand applies a force to string, but we know an ideal string, unstretchable, massless, doesn't change the magnitude of the force. So exactly, we should add gravity, normal. They don't disappear. But what do we do to make our life easier? Where do we choose the axis of rotation? Here, of course. At the physical axis of rotation in this situation, because it's actually rotating. So what number should I write for the torque of the force of gravity relative to this axis? 0. Same, we can write for the torque of the normal force relative to this axis. So there is only one torque. This is distance equal to the radius. Now this torque, positive or negative? What do you think? Negative. Nothing changed here. Axis, torque, force, torque, we call it clockwise, so negative. But acceleration also will be negative. Yeah. Angular velocity, omega, clockwise, negative. It's speeding up, which means acceleration points same way as velocity, so also negative. So these little things, kind of parts of the reasoning, important. Now this is the force, this is the radius, and the equation. Technically, if we use magnitudes and minuses to show components, well, okay, we can write this. Net z should be equal to I alpha z. Now we should write that the actual magnitude of the torque is negative. It should be equal to tension times the radius. And this variable I, like mass, is never negative and depends on the shape. And we have what we have here, disk. 1/2 mass radius squared, and that should be equal to negative 20 radians per second. We don't have to convert anything into anything. Yes? What is the difference between a cylinder and a disk? If you look straight at it, do you know if it's a disk or a cylinder? No. So there is no difference. If you make it longer and longer, you're making it heavier, putting more mass. That affects the actual value, but it doesn't affect the equation, doesn't affect the form factor. And so now we have to solve it for tension. Yeah, it should be equal to 1/2 times 10 kilograms times, we can cancel 1 R. So 25 centimeters must be converted into meters, 0.25 times 20. So since we're calculating force, it's going to be newtons. 0.25 is 1/4. 1/4, 20 divided by 4, 5. 5 times 5, 25, right? You have a calculator, so you know better. That's it. A straightforward application. Now, sometimes we have a more complicated situation. The system, this wheel is the same, but instead of pulling on the string, we have a weight attached to it. And that's a completely different system. Now it has two parts. So one part, this weight, doesn't rotate at all. So for the weight, all we have to do is just standard Newton's law we used before. But this part rotates. So for this wheel, we need to use, well, the new second law. So we will have to solve a system. And I have a specific problem. I'm not asking this question. I'm just going to solve this to see the difference. So this problem has been solved. The tension was found. Here, this is going to be a different tension, not the same. I have to, well, first of all, I'm not sure. So I have to assume the most general situation and then solve it. And if it's different, it's different. If same, it's the same. But my assumption will be different. The equation there, the equation for the spinning object is the same. Still same axis. So tension times the radius. And because it's going to be counterclockwise, should be equal to, since disk's 1/2 mass radius squared, times, I know my acceleration should have a negative component, so I write it like this, and I assume this is the magnitude of it. I just don't like writing vertical bars again and again and again. This equation is no different at all from the equation we've used here. We just need to add one more equation for this guy. Tension minus mg should be equal to m. Well, again, my acceleration points down here, so has a negative component, but this variable a now represents the magnitude of acceleration. I just don't like writing vertical bars again. I keep it in mind. And now we have to say something about connections between these two motions. And that's, again, all in the string. Since it doesn't stretch, if this end of the string travels 1 centimeter, that means this point of this rim travels exactly 1 centimeter. These motions are coupled. So distance traveled by this point is distance traveled by that point. Distance over time, speed. Changes the speed over time, acceleration. So that equation has been written before. I just want to write it again. These two accelerations, angular and linear, are coupled, are related. The same equation we used before, we called it rotational, equals linear divided by the radius. But the reason is the string is not stretchable. Now we have 3 equations to solve. 1, 2, 3. That's algebra, but actually in this particular case, very simple algebra. For example, what can I do immediately? For example, actually, this is what I can do immediately. This tension should be equal to mg minus ma. So in this case, in this question, see what we did. First, we applied a force of 10 newtons. Then we attached a weight of 10 newtons. Okay? This tension was equal to 10 newtons. But this tension should be equal to, the new one, should be equal to mg minus ma, which is 10 minus ma. And wherever ma is, it's not zero. That's why this second tension is different. Whichever has larger torque will have higher angular acceleration. So here we have 10 times radius, and here we have less than 10 times radius. So this torque will be stronger. It will lead to higher angular acceleration. Anyway, we have it solved. For tension, from the first equation, I can solve it for the same tension. It will be equal to, again, 1/2 times mass times radius squared over radius times a minus on the left and a minus on the right. I cancel them. And acceleration angular is equal to linear over r. This is what I did right here. And now, since this is supposed to be the same tension, I can say mg minus ma should be equal to 1/2 times. Lucky us, r squared divided by r and divided by r leaves no r anymore. So only mass and acceleration. Now I can collect two terms with acceleration on the same side. Mg is equal to this plus this. Acceleration is a common factor. Mg is equal to this plus this times acceleration. I can solve it for the acceleration. First of all, we can see it is not equal to gravity. It's actually less than gravity. So big M is the mass of this cylinder or disc, and little m is the mass of this weight. And as long as little m is not zero, the acceleration is not zero. So this might be a very, very heavy disk, and this might be a very, very light mass. The acceleration still not going to be equal to zero. And if you know acceleration, you can use it to calculate tension. You can use it to calculate angular acceleration. Done. Thank you very much. I'm going to pick up tomorrow from this. Don't forget the lab.